So now the third problem of our sample two of our final exam here. So it is asking us to find out the uh, to evaluate the force of some members for a trust structure. It is belonging to the chapter of structural analysis. Okay, so now we are supposed to evaluate the force member forces of member BC, EC, and EF. It is our target here. So it's so first at the beginning, it is crucially important to ensure that we are clear about what members are we going to solve here. So we are supposed to solve BC, EC, and EF here. Okay. So as long as we are clear about the members that we are going to evaluate, so it will be more clear for us to get started. So how are we going to evaluate that? Of course, so here you can go with a massive joint. However, it may not be that may require you to repeat that process for joint by joint, and it will be a little bit tedious here, and it takes a lot of time. So typically for the problem that requires you to evaluate only a few members of a trust structure, so specifically here, the problem only asks us to evaluate the forces of the three members, right? So actually, it is more convenient to use method of section, right? So by method of section here, so the idea is that imagining that you have a knife and you cut through the members that we're going to evaluate, or the members of our interest here. Okay. So, and once you cut through the structure, you cut the structure into two parts. That is the left part and the right part here. And then you can take out a part and draw the free body diagram of that, and establish equations of the part, establish equation of equilibriums of the part. So solve for the unknown forces of the components that you exposed. So here actually you can go with either the part one or part two here. But if you go with part one here, since we have the support for part one, and you will have to solve the support forces, and it is more convenient to go with part two here. Okay, so suppose that if we draw the free body diagram of part two here, and we know that, so this is a part two. Okay, joint C, joint F, and joint G here. So it is subject to two external forces here, right? So it is F1, which is 30 kilonewton here, and F2 here it is again it is actually 20 kilonewton 20 kilonewton here, and in addition to the two unknown forces here, we also have we also have the unknown force FEC here, right? And typically for the unknown forces, we will assume that it's tension, so it is going away from my joint here. So correspondingly, we also have FEC here, right? We also have FEC and FEF. Okay, so this is actually the free body diagram of the part two here. So if you look at part two, that does not involve any supports. So it is not necessary if we go with part two to solve the unknown support forces. So it is the reason why we choose to go with part two here. Okay. So, and now we can establish equations of equilibrium. Okay, so we have first summation of forces along x direction equals to 0. And what do we have along x direction here? We have FBC, right? So along x direction, it's negative here. So we also have FEC, but it is inclined but it is inclined force here. We have to decompose it, right? Okay, we are going to decompose it. And we're going to decompose it to be its x component and y component. Well, that will require us to know the slope of the line of action of FEEC here, right? Which is given by the slope of member EC here. Okay, so that is actually, so since member EC is the hypotenuse of the triangle CEF, so the slope can be specified as a small triangle here with with the base equals to 0.5 and height equals to 0.52. So it is 0.5, 0.5 here. So it is so you can also denote it as 1 as well. Okay. So it is essentially meaning that the EC is belonging to a rectangle triangle that we that is also a isolator here. Okay. So we have FEC times the we are going to have the x component of FEC here, right? So it equals to the hypotenuse times the ratio between the base and the hypotenuse, right? Okay, so that is actually our x component of FEC here. And since the x component is going going towards the left, so it is negative. We also have FEF, right? So we have FEF here, negative again. So it is actually our x component. It is a summation of forces along x direction here. Similarly, we can have summation of forces along y direction equals to 0. Okay, so along y direction we have external force, right? We have both the external forces going downward, and we also have the y component of FEC, right? We have y component of FEC here. So it is again the ratio between the head 0.5 and the hypotenuse. That will essentially be 1 over square root of 2. So it's also going downward. Okay. So please note that here actually by method section we cut off a part of the structure which is typically a rigid which is typically a general rigid body here. So we have a three equations of equilibrium. So the third equation is summation of the moments of forces about a point equals to 0, right? Okay, then we have summation of moment about a point equals 0, and about which point you would like to take the summation of moment here, of course. So typically we go with the point that with the most numbers of line sections of unknowns line. It is a line of actions of the unknowns crossed, right? Here it is actually C, because if you look at C, we have a line of actions of FBC, FEC all across the C, right? So that will only have FEF in the equation. So that lowers the number of unknowns in our equation here. And for the summation, so for the summation of moment about C, we're going to have first FEC times the distance between the line of action of FEC to C, which is actually 0.5, right? Okay, positive or negative here. Since now it is rotating about C clockwise, right? Clockwise. So it is a negative here. We also have, okay, so now if you look at the external force of 30 kilonewton here, since the line of action crossed the C, so it will not appear in the equation here, right? Okay, it is because the moment arm of F1, the 30 kilonewton here, it is equals to 0. and we only have, okay, 20 kilonewton here, right? So times the distance between the line of action to C, which again equals to 0.5, right? Okay, okay, so is it positive or negative here? Okay, so again, it is clockwise, so it is negative here. Now we have three equations, and we can go ahead to solve the equations. So here it is more convenient to solve the equations second and third equation first, and then substitute the unknowns that you solved to the first equation, right? Okay, so now we can solve by the third equation. You are going to have FEF equals to negative 20 kilonewton here, right? And by seeing that it is a negative, we mean it is actually compression, right? It is compression here. Okay. So by the second equation, FEC equals to, okay, by the second equation, and we know that FEC will equals to, it will equals to a negative of 50 kilonewton times the square root of 2. Right? So it will be negative 70.7 here. So kilonewton. And again, so the negative here meaning that it is compression. So substitute FEC and FEF back to the first equation. You're gonna have FBC equals to, okay. So we're gonna have FBC equals to, so it is FEC divided by square root of 2, then plus FEF, it is a 20 here. Okay, it is actually a positive number here. It is a 70 kilonewton here, and positive number meaning that it is a tension, right? So we can convert it to be 20 kilonewton compression, 70.7 kilonewton compression, and 70 kilonewton tension here. So now it is actually the answer for the for this truss structure. So it is a 20 kilonewton here compression. Okay, it is so the direction or identifying that it is a compression or tension, it is equally important as identifying the magnitude of that, because for structures we know that when the member subjected to tension or compression, the behavior and the failure mode of truss members, it could be completely different. Okay. 70. Okay. Okay. So this problem here examined our knowledge and skill side for solving trust structure here. So essentially it is asking us to evaluate the unknown member force of a few members of the trust structure. Typically, to evaluate that, it is a method of section is more appropriate here. So it is more convenient. So and typically the idea is that we first to identify the member the members of our interest here. So all the members of which the force that we are going to evaluate. And then we imagine that we have a knife to cut through the members, cut the cross structure into parts. And we take out the part and to perform force analysis for the part. Since the member forces will appear to be external forces for the part, it will by solving the parts or equation of equilibrium of the parts, we can solve the unknown member forces here. Okay, so generally how we perform method section for the structure here.